My name is Gustavo, and like Tim said, I read this paper named Comprehensive Study on the Energy Efficiency of Java JavaScript in Collections, and this is a joint work with Fernando Liu, Fernando Castor, and David Liu from all these universities, Binghamton, the State University of New York, and the Federal University of Pernambuco. First of all, I have a very quick disclaimer because today my son is turning 8 months, so I would like to say, hey, I love you, son. Thank you. So this work has a couple of motivations, and the first motivation is, of course, about energy consumption, which is not even a problem for your cell phone and your tablets, but it's also a problem for computers and data centers. And the second problem here is multi-core CPUs, because they are everywhere. If you use your cell phone, it might be a multi-core CPU. And the complexity here is that you do want to use the most cores that you have, but you also want to reduce the energy consumption of those cores. So they are two driving forces going on opposite directions. And the third motivation is data structures, because they are the fundamentals of computer programming. Of course, you should use data structures if you want to write any kind of program. So let's say you are a Java programmer, and you have this statement here. So what you can do, there are a couple of options for this statement here. So let's say you choose ArrayList, and ArrayList is fine. It implements the interface, you don't have any compiler error. But what happens when this object here is used by more than one thread? What happens? So that is what happens. So you have concurrency problems here. So then when you figure out that you have concurrency problems, you go back to the documentation and you try to find new implementations that are thread safe. So let's say you now choose vector. And vector is good. Vector solves the problem, vector implements the same interface, and what happens when this object here is used by more than one thread? So nothing happens because vector is thread safe. So now let's say you want to go to the source code and see what's the difference. So this is the vector source code, and if you can see most of the public methods, they are synchronized. That's good because it solves the problem, but it creates a new problem, a performance problem. So when you realize that, you go back to the documentation. Let's say now you choose another implementation. So this implementation is good, no compiler problems, and what happens when you have multiple threads? Nothing happens. And you go back to the source code. And the source code says that when you are reading operations, when you are doing get operations, you don't have any kind of synchronization. So that's good, right? But when you are writing, you are doing writing operations, you not only have the log statement in the beginning of the method, but you also have a copy of the entire data structure for each new element that you insert. So it creates another problem for yourself. So the question is, you have several kinds of implementations, several kinds of collection families, and which kind of implementation you should use, right? So this is a very common question. So the point of this paper here is to ask the same question, but how about energy consumption? You have all these implementations, they are all different, and what is the energy behavior of them? So to provide the answer to this question, we studied 16 collections grouped by three interfaces. So for each interface, we selected a non-thread safe implementation to work as our benchmark and several other thread safe implementations. We also selected this compute hash map implementation from version 7 and version 8 of the Java JDK. We did that because the version 8 was a completely rewritten implementation. So we saw that and we thought how it will behave in terms of energy consumption. And we did that for 3 kinds of operations: traversal, operation, insertions, and removals. And we did that for 2 kinds of environments. We use as AMD CPU, and we use it an Intel CPU. And we also did 2 kinds of 2 different energy measurements. So we used a hardware-based meter that we plug it the cable in the CPU cable of the CPU, and we also use a software-based meter, which is a software that we install at the server that does the measurement for us. So if you guys want to know more about the details of the experiments, I would invite you to go to the artifacts track that will take place on Friday. If you want now talk about the results, these are the overall results for the list implementation. There's a lot of figures here, and if you want to look closer for just one of them, this is one figure, and all bars here represent a given collection. So this one is a list, this one is vector, this one is collection synchronized list. So each bar also means energy consumption, and the line means power dissipation. The bars on the bottom, they are actually divided by different kinds of energy measurements. So the top parts of the bar are actually DRAM energy consumption, and the middle part is on-core energy consumption, and the bottom part is CPU energy consumption. So if you go back to the results, we may see that in the top we have the AMD CPU, and in the bottom we have Intel CPU. So for now, what we can see is that the collection, the implementation that consumes the least energy consumption are actually the non-thread safe implementation, which makes sense because there is no synchronization overhead, then less energy consumption. And if we compare vector and collection synchronized lists, they are actually similar in terms of energy consumption. And if you go to the source code, you might see that the implementation of these 2 collections, they are very similar. The only difference is that collection synchronized list does not synchronize on the iterator, and vector does synchronize. So if we move forward to maps, we may see that the same thing happened here. So the non-thread safe implementation consumes the least energy when doing traversal operations. And if we compare these 2 guys here, the first one is hash table, and the second one is compute hash map. They also have similar behaviors, but the problem here is that hash table is a single lock based data structure. You will have only one lock for the entire data structure. And compute hash map actually has different kinds of lock strategies to be more efficient in terms of performance. But if you look for compute hash map V8, which is the last bar, we can see that it is actually better than the previous implementation. And it also happens for insertions, and also happens for removals. But the most interesting thing here, in my opinion, is that for these 2 guys here, the compute hash map V8 implementation consumes less energy than the non-thread safe implementation. It means that if you are writing a program and you don't care about concurrency, you can also use compute hash map V8 to save energy. So with these finds, we did a case study. And the case study, we used the Da Capo benchmark suite, which is a framework with non-trivial benchmarks. So we chose 2 of these benchmarks, and the first one was Tomcat. And Tomcat is a web server, and it has more than 170,000 lines of code, and it has more than 300 hash tables, right? And the second benchmark was Zela. And Zela is a benchmark that parses XML documents into HTML documents, and it has more than 180,000 lines of Java code. and it has more than 140 hash tables. So we did that thing. For each hash table instance, change it for concurrent hash map 1. Do the measurements, and after that, do it again for concurrent hash map V8. Right? We just changed the implementation. So these are the results for Tomcat. And as we can see, transforming from hash table to concurrent hash map, we saved about 12% of energy just doing this kind of transformation. And then, when we changed from hash table to concurrent hash map V8, we saved 70%. So just doing a trivial modification, we saved a lot of energy. And we have similar results for Zeta. And Zeta, we had 5% for concurrent hash map and about 9% for concurrent hash map V8. So, you guys may be wondering, if that's so good, I'll change the hash table interface to concurrent hash map once, right? Makes sense. But we found that there are some kinds of challenges, challenge transformations that you cannot always do that. So I will talk about only one of them now, and if you want more details, you can read the paper too. So this is the organization of the code. So hash table implements the map interface, and concurrent hash map implements the map interface. But the problem here is that hash table also implements the clonable interface. So it means that if you have this kind of code here, I don't know if you guys can see, but is object.clone in the second line. It works fine when you have a hash table because it implements the clonable interface, but it does not compile when you are using a concurrent hash map. So you cannot change naively all kinds of instances to hash table. In fact, for those guys who like refactoring, you may be thinking about improving or creating new kinds of refactoring tools. So in this paper, I think we have two takeaway messages. And the first one is that small changes can have great impact when it comes to energy consumption. So we just changed these few implementations to another kind of implementation and saved some kinds of energy consumption. And the second message is staying up to date with the new release of the Java Unity Concurrent library, because we saw that when you changed it from concurrent hash map to concurrent hash map V8, we saved even more energy consumption. So in summary, I believe that we did a kind of comprehensive study using two computers, two kinds of energy measurements, several benchmarks, and we found some stuff like the thread-safe implementation consumes less energy than the non-thread-safe implementation. We also did case studies with two non-trivial benchmarks, and we also found that we can save energy in those kinds of applications. And we also found some refactoring challenges for those who like to join us. So I would like to thank you for your attention now, and I will be more than happy to take some questions.